meant by the term ionization energy of an element. So this is the minimum amount of energy required to remove 1 mole of electrons, plural, because we are using 1 mole electrons from 1 mole of gaseous atoms to form 1 mole of positively charged gaseous ions. The only reason why I'm using these ions, atoms, electrons is because I'm using 1 mole throughout. If you can also use 1 electron from 1 gaseous atom to form 1 unipositively charged gaseous ion. Okay. Write an equation to show first ionization energy of magnesium. So now, if I have magnesium, okay, in gas form, because that's what we said, a gaseous atom or gaseous atoms, and the first ionization energy, that means I lost only 1 electron, so we are going to form with a charge of plus only, plus an electron. So this is the thing, write an equation to show the first ionization of magnesium. Gas, symbols written very well, the sharp edges on magnesium, some of the stuff which are marked. Okay. Now the second and third ionization energy of magnesium are 1450 kilojoules per mole and 730 kilojoules per mole. These are actually positive. It's an endothermic reaction. Minimum amount of energy required. Give a reason for the large difference between the second and third ionization energy of magnesium. If I'm to write the electronic configuration of magnesium, which is magnesium is 12, right? 1s2, 2s2, 2p6, 3s2. These are 10 plus 2. Now, magnesium loses the first electron, right, from the outermost energy level. So now, let's remove this 2 and we put 1. Okay? The concept behind the losing is half filled or fully filled orbitals and energy levels are stable. So now we are looking for this. Is this 3s1 half filled or fully filled? It's half filled. Is it stable? Yes, it's stable. Okay. Now, this is the first ionization energy, right? This is magnesium plus. Now, what if we lose another electron? Now, this one becomes 3s0, isn't it? Now, we are coming to a fully filled 2s. I mean, this second energy level here. It's fully filled. So, to remove an electron from the next one, it will be 7730. So now, give a reason for the large difference between the second and third ionization energy of magnesium. So when the second electron is removed, actually the phrasing. So the second electron is removed from a half-filled 3s orbital, right? Which is, we can say, thermodynamically unstable. while the third electron was removed from a thermodynamically stable, fully filled 2p orbital. That is why there will be a large difference, because now we are having a 2p6, which is a fully filled orbital. Okay, let's continue. Name one reagent that can be used to distinguish between each of the following pairs of compounds and state what would be observed in each case if the reagents react with the components. Basically distinguishing, right? Now, first of all, which group are these two? They are carbonyl compounds, right? And especially ketones. Can we use the ketone test? No, because both of them they are ketones. Now let's go on to see another difference. I'm seeing CH2, CH3 here, but I'm seeing only CH3. That means there is this methyl group adjacent to the carbonyl group. Which test can we use? Iodine solution, iodoform, right? Iodine solution and dilute sodium hydroxide solution. So now the one which has this one is going to give us yellow precipitate, while the other one is going to give us no observable change because the methyl group is not adjacent to the carbonyl group. Okay, next is we're having a compound like this. These are alcohols, right? But now different classes. So they are just telling us Lucas test. In Lucas test we have anhydrous, zinc chloride and concentrated hydrochloric acid solution. 2022 paper 3. They tested us on this compound here. So now what happens in Lucas test? This one we are going to see no cloudy solution formed at room temperature. However, this we are going to have a cloudy solution formed immediately. Now this one is about primary and tertiary. What about a secondary one? So let me just write a side note here. Secondary, we are going to have cloudy solution formed after 5 to 10 minutes. This one you can use it in theory, but in practical you have to specify a particular time because they expect you to be doing a practical with a clock. You cannot put a time range there. Okay, let's go on. The osmotic pressure of a solution containing 1.4 gram of polymer X per 100 centimeters cubed of solution is 1200 Newton meters squared. at 25 degrees Celsius. Calculate the relative molecular mass, RMM. The first thing when approaching this question is underline the key things. 1.4 grams, right? So mass equals 1.4 grams. Volume is 100 centimeters cubed. Pressure is 1200 centimeters squared, and the temperature is 25 degrees Celsius. Straight away when approaching this question, they expect you to be knowing this formula here. PV equals to nRT. It actually carries a mark, half or full, whichever, depending. And they want you to find the molecular mass. So pressure, there are conditions when the molar gas constant is 8.314. Okay, so when we are using this molar gas constant, there are some of the conditions which you have to follow. Is that mass should be in grams, pressure should be in pascals stroke Newton per meter squared, and temperature should be in kelvins. Okay, so now our mass is in grams, but actually even volume should be in meters cubed. The easier way to understand, to easily memorize this, is that this Newton per meter squared, meter volume should be in meters. Okay, so now pressure is 1200. Pressure is okay. Volume is in centimeters cubed. We want to convert it to meters cubed. So 1 centimeters cubed equals to 10 to power negative 6 meters cubed, right? Because 1 meter equals to 100 centimeter, right? That means 1 centimeter equals to 10 to power negative 2 meters, isn't it? So if I'm going to cube each side, mathematically it will be powers will multiply, right? So negative 6 meters cubed. Okay, so now I will just multiply this 100 by 10 to power negative 6. So now our volume is sorted. Let's go to the other side. N is number of moles. So moles is what? Mass out of RFM, right? So mass is what? 1.4 divided by relative molecular mass. Let's write all of it. Avoid short forms in paper 1. Times molar gas constant, which is 8.314, times 25 plus 273. That's how we change it to kelvins. So finally, relative molecular mass will be, okay, so relative molecular mass will be 28905.00667. Since it's relative, no units. Okay, and the mass is really big because it's a polymer. Polymers are a collection of monomers, right? So obviously the mass will be big. Determine the number of monomers in X. The molecular mass of monomer of X is 28. So there's just one number of monomers, right? So number of monomers will equal to, what is the relative molecular mass of polymer? 28,905.00667 divided by 28. So you can press the calculator again and get the answer. I think it should come out to approximately 0.322. We cannot have decimals in the number of monomers, so we can round off to the next bigger one, 1032 monomers.